Right, so today I'm just going to be talking about in this guest lecture about how we can apply quantum mechanics and quantum computing for machine learning applications. Just how this new field in computing can be used to sort of augment what we already know about machine learning and some cool applications of this and some cool architectures from this. So because of how much there is to learn about quantum computing, a good amount of this lecture is going to be dedicated to sort of covering the prereqs for what you need to know to understand the quantum computing behind the machine learning, right? But then after that, we can actually get into the really cool machine learning applications of this. So yeah, let's just jump right in. So the first thing you guys might be wondering is why? Why should we go quantum for machine learning, right? Well, at the end of the day, the only real reason is because of how powerful quantum computing is. There's really no other reason. So I'm sure you've all heard about Google's quantum supremacy experiment a few years back and how they established their quantum supremacy, established how they were able to solve a task on a quantum computer that was basically completely infeasible on classical computer hardware. And they did this by using 53 noisy qubits, and noisy in this context just refers to how there's uncertainty in physical quantities that are of quantum origin. It's nothing too confusing. And they used 53 noisy qubits to demonstrate how they could perform this specific calculation in 200 seconds on a quantum computer that on a classical computer would have taken 10,000 years. So yes, quantum computing is incredibly powerful, and this has a lot of implications for machine learning that we'll get into later in this lecture. So let's talk about NINTQ technology, because that's very important to understand for quantum machine learning, because most machine learning techniques that are used in using quantum computing right now rely on NINTQ technology. So the Google supremacy experiment marked the beginning of the noisy intermediate scale quantum or NINTQ computing era. And this is an era where NINTQ technologies become more and more common. So when we're talking about quantum computers, when you hear about quantum computers and how crazy powerful they are, that's usually referring to fault-tolerant devices. And these are devices that are just really powerful. They're able to factor really large numbers. They're able to crack security and do all those crazy things, right? But the power to be able to do these things comes with a cost, all right? To solve a factoring problem, factor really large numbers that isn't feasible for classical computers, that requires millions of qubits because you need a lot of overhead. You need a lot of extra qubits in order to do error correction. Because the reason for this is because most algorithms we know for this are really extremely sensitive to noise. And so you need to have this overhead of millions of qubits in order to do error corrections, in order to make sure we're not dealing with any noise that'll ruin our calculations. And so here's the thing. Even though it takes millions of qubits to do these really powerful tasks, any task that uses just more than 50 qubits, like Google's quantum supremacy experiment, that many qubits is enough to be beyond capable of being simulated by classical computers. And so now that Google's done exactly this, right? They've used more than 50 qubits, right? They've done this sort of proof of principle showing quantum supremacy. So now we're in this weird era where we know that quantum devices can do things that classical computers can't, but they don't have enough qubits yet to be able to provide truly fault-tolerant implementations of algorithms that we know about. And so this is why John Preskill coined the term noisy intermediate scale quantum, or NINTQ, to describe this era. The noisy here just means that we don't have enough qubits for error correction, right? And this goes back to earlier where I said that, a quantum noise is just when there's uncertainty because of the nature of being quantum, right? And so this noise/uncertainty leads to errors, right? And that's why we need such a large number, millions of qubits, in order to be fault tolerant, in order to mitigate these errors. And the intermediate scale part of the noisy intermediate scale quantum coined term, that intermediate scale comes from the fact that we're not necessarily using a small number of qubits, right? 50 isn't really a small number, but it's also nothing compared to millions of qubits, right? So that's why we just use the term intermediate there. And so what applications does this NINTQ technology have? Well, first, machine learning. We'll get into that later in the lecture, but these questions aren't fully answered because there is a lot of research on NINTQ technologies, but there's also a lot of more research, I'd argue, maybe, on fault-tolerant devices, theoretical fault-tolerant devices that use millions of qubits that don't even exist yet. There's a lot more research on that than on NINTQ technologies, and so we don't fully know the applications for NINTQ technologies. And John Preskill actually theorized that it might take up to 30 years or more in order to actually find practical applications for NINTQ technology. But that sort of sucks, but it's still really cool. Now, before we jump into quantum machine learning, like we finally start the main part of this lecture, I'm going to just quickly explain what qubits are. That'll take like 1 minute. It's nothing crazy. So qubits, simply put, are very similar to regular bits, right? Which classical computers use zeros and ones. Qubits are like bits which use zeros and ones, except they're a little special because they can be put into a superposition, and they also share entanglement with each other. So quantum superposition is really simple. All it means is that if a physical system it can be in one of many configurations, then the most general state it can be in is a combination of all these possibilities, all these configurations. So explaining that simply, Schrodinger's cat, right? Simultaneously alive and dead until you actually open the box. That's all superposition really is. Quantum entanglement is this phenomenon where entangled particles are able to stay connected, meaning that if you perform an action on one of the entangled particles, the same action gets performed on the other, or like the other particle also gets affected. And this happens no matter the distance between the two particles. You do one thing to the one particle and same thing happens to the other. It's pretty cool. And these two things are sort of the basis for how qubits are so powerful and how they're able to do so many cool things in quantum devices, and how these quantum computers are able to do things that classical computers simply cannot. Now let's talk about quantum data. We're actually going to start the quantum machine learning part of this lecture, the part that you probably actually care about. Okay, so to understand quantum machine learning, we need to understand the two concepts that it's built on, those being what we're going to talk about on this slide, quantum data, and then hybrid quantum classical models, which we're going to talk about on the next slide. So let's talk about quantum data first. Quantum data is basically just any data source that comes from a quantum system. So what does this mean? Maybe that refers to data generated by quantum computers, like the data that was gathered by the Sycamore 53 qubit processor, which was used in the Google quantum supremacy demonstration. So the data generated by that processor, right, that is quantum data. Now, quantum data exhibits the two principles mentioned in the previous slide, superposition and entanglement. And this leads to what are known as joint probability distributions. All right. All that means is that's the likelihood of more than one event occurring at the same time. And so joint probability distributions require an exponential amount of classical computational resources to demonstrate, to represent, to store. And so the quantum supremacy experiment showed how it's possible to sample from this extremely complicated and complex joint probability distribution of a 2 to the power 53 Hilbert space, and a Hilbert space is just in mathematics when we're trying to sort of describe what happens in more than three dimensions. The quantum supremacy experiment, it showed us how it is in fact possible to sample from this extremely complicated distribution of Hilbert space. The quantum data generated by NINTQ processors, all right, they're usually very noisy, and they're typically entangled just before the measurement occurs. And so we have heuristic machine learning techniques that are capable of creating models that are able to maximize the amount of extraction of useful classical information from noisy entangled data. But these are still in their infancy. They're not, crazy developed yet. This is a relatively new field. TensorFlow Quantum, the library, is actually one of the most popular libraries for researching this field because of how, TensorFlow is really popular, so it makes sense. That's not crazy. So this TensorFlow Quantum library is building a lot of opportunities for people to improve existing quantum algorithms or discover even newer quantum algorithms. There's a bunch of stuff we can do with quantum data. I'm going to sort of just skim over this so we can jump into the actual models. But with quantum data, you can do stuff like, for example, chemical simulation, quantum matter simulation, quantum control, quantum communications networks, quantum meteorology. There's a lot of really, really cool stuff that you can do with quantum data. All right, so now let's move on to hybrid quantum classical models. This is where stuff gets interesting. So we're going to explore how a classical neural network can be partially quantized in order to create a hybrid quantum classical neural network. So to understand that, let's understand what a quantum model is. So quantum models represent and generalize quantum data, all right? Now, NINTQ quantum processors are still fairly small and noisy, and so because of this, quantum processors aren't really able to generalize quantum data using only, quantum processors alone aren't able to do this. Quantum processors need to work in tandem with classical coprocessors like GPUs, CPUs, and TPUs in order to actually create quantum models. All right. Now, I want to just clarify really quickly that in TensorFlow Quantum, when people are working with qubits, they're not using actual qubits that exist in superpositions and entanglements and all that. They're using a library called Cirq, and in Cirq, a qubit is nothing more than an abstract object, all right? It's not like an actual qubit. It doesn't like have those weird state stuff. It doesn't do anything crazy because, I mean, the only way to be able to do that would be if you had a quantum processor, and I'm not sure how many of us actually have access to those on a regular basis. So yeah, that makes sense that TensorFlow Quantum doesn't actually use real qubits. And to understand hybrid quantum classical models, we need to quickly understand how quantum neural networks, or as they're sometimes called, parameterized quantum circuits, we need to understand how they work. So quantum neural networks are used to describe a parameterized quantum computational model that's best executed on a quantum computer. That sounds fancy and it might be a little hard to grasp, but I think in the next few minutes, I'll be able to clarify it a little more in all of your heads. So to create a quantum classical hybrid neural network, what you have to do is you can implement a hidden layer for our neural network, okay? A hidden layer for our neural network. And this hidden layer, like we said earlier, uses a parameterized quantum circuit. And so by parameterized quantum circuit, what we mean is it's a quantum circuit where the rotation angles, all right, the rotation angles for each gate are specified by the components of a classical input vector, So we're using classical input vectors to help with this quantum hidden layer. And so what's going on is the outputs from our neural network's previous layer will be collected and used as the inputs for the quantum parameterized circuit, okay? The measurement statistics of our quantum circuit can then be collected and used as inputs for the following layer. And so this is a simple example right here. And I hope that explanation just now made sense. Basically right here, sigma is just the activation function, and hi, right? H1, H2, hi is just the value of neuron I at each hidden layer. And then R of H of I, right? That represents that rotation gate I was speaking about earlier, right? About an angle equal to Hi and Y. So it's the rotation gate about an angle equal to Hi and Y. Sorry, I'm speaking a little too fast. I might be getting a little confusing. Let me slow down and explain it properly. R of Hi represents any rotation gate about an angle equal to Hi. And Y is the final prediction value generated from this hybrid network. I hope that made sense. So now we need to understand backpropagation though, right? Because obviously backpropagation for these hybrid networks is going to work very differently from classical machine learning. And that is partially true. It does work a little differently. So it's sort of a black box, all right? Because we need to use gradient descent for backpropagation, right? As you guys probably all know. And so how that works, we're going to go into more depth on the next slide. But essentially, a sort of quick overview is that if we view quantum circuit as a black box, then the gradient of the black box with respect to its parameters can be calculated as follows with this right here. And essentially what we're doing is if theta represents the parameters of the quantum circuit and S is this macroscopic shift, then the gradient is just the difference between our quantum circuit evaluated at theta plus S and theta minus S. And so we're able to systematically differentiate our quantum circuit as part of a larger backpropagation routine. And so this is called, this closed form rule for calculating the gradient of a quantum circuit, this is known as the parameter shift rule. And so let me explain gradient descent in a little bit more depth on the next slide, all right? So quantum gradient descent, all right? Again, I know you guys probably all know a lot about standard gradient descent and standard natural gradient descent, but I'm still going to give another quick overview over it because I think it's important to help understand how quantum natural gradient descent works and how it's a little more unique. So we're going to do that. So the most successful types of quantum algorithms for this NINTQ technology, where it's noisy quantum hardware, right? They're called variational quantum algorithms. And what they are is It's when we have a low depth parameterized quantum circuit or a quantum neural network like earlier, and we choose it and we use its measured expectation values to create a cost function. And then we just use a classical optimization loop and then use that to find the set of circuit parameters for a quantum device to minimize the cost function. So we're basically just applying classical optimization techniques. And some popular examples of algorithms include variational quantum eigensolver and quantum approximate optimization algorithm. And so what these are, all right, are just these are simple. So QAOA, quantum approximate optimization algorithm, is a toy model of quantum annealing, and it's used a lot to solve problems in graph theory. This algorithm in classical optimization is used for classical optimization of quantum operations in order to maximize objective functions. So that's what it's used for machine learning. Then the VQE algorithm, the variational quantum eigensolver, right? That is used in classical. It applies to classical optimization in order to sort of minimize. All right, and so that those two algorithms are really cool, and they're optimization algorithms. Now let's explain quantum gradient descent. So again, I'm going to review standard gradient descent, which I know you all probably know really well, but still, for the sake of making the quantum explanation easier, I'm going to do it. Sorry. So quantum gradient descent. In standard gradient descent, each optimization step, right, is given in this equation right here. And an L of theta is just the cost as a function of the parameters theta, and n is the learning, and here, right here, this is the learning rate, or the step size. And in essence, each optimization step calculates the steepest descent direction around the local value of theta t, in the parameter space. And what we're doing is we're updating theta t to theta t plus 1 by this vector. That was a sort of convoluted explanation, but standard gradient descent, all we're doing is we're trying to slowly find the steepest, we're finding the steepest descent direction around this local value, and then we're going to keep on doing this to minimize our function, our L of theta function. Then the problem with this is that each of these optimization steps, each t time step, is very, very, very strongly connected to Euclidean geometry, or on the parameter space. And the problem with this is that different parameterizations can distort distances within the optimization landscape. So let me explain what this means, right? And I'm sure you guys already understand this, but again, I'm just going to review it. So let's say, as an example, right, we consider the following cost function, L of theta, we were just talking about, right? And we parameterize it using two different coordinate systems, this one and this one. As you can see right here, if we perform gradient descent in the theta 1, theta 2 parameter space, we're updating each parameter by the same overall Euclidean distance in Euclidean space, all right? And we're not taking into account the fact that the cost function might vary at a different rate with respect to each parameter. And so this causes the optimization to struggle to find, it might even miss the minimum altogether, and that's a problem, right? Now, if we instead perform a change of coordinate system, all right, a reparameterization of the cost function, we might find a parameter space where variations in this function L are similar across different parameters. So this is the case if we use a different parameterization with phi1 and phi2. Here, the cost function is unchanged, right? But we have this nicer geometry. And so because of this, we're able to perform gradient descent in a way that's much nicer, and we have a much more informative step size. And this leads to a faster convergence rate, and now we can help avoid optimization being stuck in a local minima. And so as you can see, this reparameterization makes a very big distance. Big difference, not big distance. Let's not get confused there. But what if we want to completely avoid gradient descent in the parameter space altogether? Well, how about this? Let's consider the optimization problem as a probability distribution of possible output values given an input. All right, and then a better approach is to perform the gradient descent in this distribution space where it's dimensionless and invariant with respect to the parameterization. And so as a result, each optimization step will always choose the optimum step size for every parameter regardless of the parameterization. And this is very, very, very nice for us. In classical machine learning, that process is known as natural gradient descent, and it's given by this equation right here. I hope you guys can see that properly. It's a little pixelated, but I think it should come clearly. So natural gradient descent, it was introduced like 2 decades ago in like 1998, right? You guys probably all know that, but we can just modify the standard gradient descent formula just slightly differently to make it look like this. It's very similar looking, but there's a very small difference. And so the only real difference is that we have this F, which is known as the Fisher information matrix. And the Fisher information matrix just acts as a metric tensor. And a metric tensor, all that is a function which tells us how to compute the distance between any 2 points in a given space. And so because of this nice Fisher information matrix, this metric tensor, we're able to transform the steepest descent in the Euclidean parameter space into the steepest descent in the distribution space. All right, you catch all that? Now it's time for quantum natural gradient descent. This is going to be the main focus of this lecture. And once we're done with this, I'll just sort of quickly tell you guys about some applications about quantum machine learning, and then we can end the guest lecture. So in a similar vein, right, with it's been shown in standard Euclidean geometry that this is suboptimal. It's been shown that, let me slow down. In a similar vein, right, for quantum gradient descent, it's been shown that standard Euclidean geometry is suboptimal for the optimization of quantum variational algorithms. All right. So see, the space of quantum states possesses this invariant metric known as the Fubini-Stugy metric tensor. And this is represented by a matrix G. And this can be used to construct a quantum sort of, something that's a quantum sort of alternative, not a quantum alternative, a quantum analog, all right? It's very similar to how natural gradient descent, except it's now quantum natural gradient descent works. It's very similar to standard natural gradient descent, except now we're dealing with the quantum world. And so in this equation, G plus refers to the pseudo-inverse, all right? And the pseudo-inverse is simply just a generalization of the inverse matrix. And the Fubini-Study metric tensor that we're talking about here has lots of interesting properties. For instance, it reduces the Fisher information matrix we were talking about when information is encoded in an orthonormal basis. And on top of that, it also has a few intriguing theoretical connections that I'm not going to go over with imaginary time evolution variational algorithms and a bunch of other complicated quantum computing stuff that I'm not going to go over in this lecture. So the full Fubini-Study metric tensor can't really be evaluated on modern quantum hardware yet, right? This right here in this equation, right? The Fubini-Study metric tensor I was talking about, it can't really be evaluated properly on the modern NINTQ quantum hardware yet. But what we can do is compute a block diagonal approximation. So we can get something that's really close to that. So let's consider this variational quantum circuit as an example. All right, this right here is what we'll use as an example to explain the block diagonal approximation. So each layer in this variational quantum circuit corresponds to a diagonal submatrix of the Fubini-Study metric tensor. All right, and the dimension of each is determined by the number of parameters in the layer. So let's look right here. Well, obviously there are 2 layers and each layer has 2 parameters. And so what does that tell us? Well, that means that the block diagonal approximation consists of 2 2x2 matrices. And so now, boom, we got it. We can now construct a block diagonal Fubini-Study metric approximation. And now we can perform quantum natural gradient descent. And so now we have a fundamental basis for how quantum machine learning works. We're essentially just using the ideas we know from standard machine learning and we're applying them here. We're just using regular gradient descent, regular natural gradient descent, and we're making it quantumified, right? So now we can do it with quantum hardware, and so we can do all these cool things. And going back to just how cool hybrid quantum classical models are, I just want to quickly go over some applications that it can be used for. So let me do that quickly. So some cool applications of hybrid quantum classical models, all right? So since what we're doing is we're combining classical models with quantum models, this gives us a lot of extra leeway in a lot of things that we couldn't typically do. For example, All right. As an example, with quantum machine learning concepts, with using quantum machine learning, we're able to do a lot of things that are being researched right now. For example, we're able to enhance current NISQ algorithms. All right. By using the hope of using machine learning here is what we're doing is we're using classical machine learning techniques to enhance NISQ algorithms. So the hope here is that the techniques from classical machine learning can maybe enhance the current understanding of quantum computing. So there's meta learning for quantum neural networks via classical recurrent neural networks. And so in this example, with meta learning for quantum neural networks via classical recurrent neural networks, what's going on is a recurrent neural network, a RNN, is being used to discover how optimization of control parameters for the quantum algorithms, quantum optimization algorithms I talked about earlier, right? QAOA and VQE. These recurrent neural networks are being used to show how they're actually more efficient than regular optimizers. All right, that isn't anything too crazy, but it's a really cool use of how we're able to use recurrent neural networks, how we're able to use standard machine learning to learn more about quantum computing. Then the next research paper I want to talk about quickly is about how we're using reinforcement learning to help mitigate errors and produce higher quality quantum gates. And so, yeah, right now, a lot of what quantum machine learning concepts are being used for is primarily just to improve our understanding of quantum computing. Not so much to do cool quantum machine learning things and cool quantum machine learning tasks, but more to understand what we know about quantum computing. And that's all right. And the next thing is the next main usage of quantum machine learning techniques is for the modeling of quantum data. All right. And so, I just want to make clear that what I was talking about earlier with the classical machine learning to enhance NISQ algorithms, that doesn't necessarily use hybrid quantum classical models. I don't want to confuse you guys, but it's just talking about how we can use standard conventional machine learning for improving our understanding of quantum computing. So I don't want to cause any confusion. Sorry about that, if that was a little convoluted just now. So then the next big application of what quantum machine learning techniques are being used for is how we're using quantum data and we're modeling quantum data using quantum circuits. All right. So classically, modeling quantum data is possible, right? But only if you have an exact description of the data source. The problem is that that's not always possible. So in order to solve the problem where we don't have an exact description of the quantum data source, we try to model on the quantum computer itself and measure and observe important statistics. And so there's this paper about quantum convolutional neural networks that showed how a quantum circuit was able to be designed with a structure very similar to regular convolutional neural networks, and how they're able to use this to detect different topological phases of matter. And so the quantum computer holds the data and the model, all right? And then the classical processor sees only measurement samples from the model output and never the data itself, if that makes sense. Essentially, what they did was they just used quantum convolutional neural networks, which are very similar to convolutional neural networks, in order to do this task. Now, in another paper known as Robust Entanglement Renormalization on a Noisy Quantum Computer. That's a long title. And I just want to say that all of these papers I'm talking about right now, if you go to the TensorFlow Quantum website, you'll find links to all of these papers that you can read on your own time. They're really interesting. And if you're interested at all about what I've been talking about in this presentation, I really recommend that you take a look at these papers. So in that paper, I just said the name of Robust Entanglement Renormalization on a Noisy Quantum Computer. What they did was they compressed information about quantum-made systems, body systems, using a machine learning model. So yeah, that is the gist of quantum machine learning. It's a very quick introduction and overview. I didn't go crazy in depth into a lot of the research because, I mean, simply put, quantum computing is a really, really, really complicated topic. There's a lot of crazy research going into it. And I just didn't think there would be enough time to fully explore all of the concepts in quantum computing enough to give us a really good understanding of even more quantum machine learning things. But I hope that today's guest lecture was able to give you all a nice introduction into how quantum computing helps aid with machine learning stuff and how it can be used for a lot of cool stuff in the next 30 years or so. Yeah. So thank you.